Lewis structures and resonance structures by Adarsh, Abhinav, and Amir. Lewis structure diagrams that show the bonds and lone pair structures of a compound. To make them, you should consider the valence electrons. You count the number of valence electrons available. For example, in CH4, carbon has 4 valence electrons and the 4 hydrogens have 4, so 8 in total. You should use all valence electrons available. Add or remove extra valence electrons based on the charge of the compound. The octet rule. This is a rule that states that atoms want to have 8 valence electrons around them, besides hydrogen, which wants 2, to fulfill a duet. Electronegativity. H can never be the center atom. For the central atom, you pick the one with the lowest electronegativity. Bonds. They represent two shared electrons and can have double or triple bonds. Count them as two valence electrons for the bonded elements. Lone pairs. Electrons. These are electrons not used for bonding outside of the atom. In water, oxygen has two lone pairs, as you can see right here. Here's an electronegativity table that shows the periodic trends for electronegativity. It increases as you go up and to the right. Make a Lewis structure diagram for HOCl.
Alright, resonance structures. Resonance describes the fact that there can be multiple dial configurations of a Lewis structure for one compound. Resonance structures. Because the bonds essentially move around, we need resonance structures that depict all the different bond configurations, as shown with CO32- and bond order. To calculate the bond order for a resonance structure, we take the average bond order for the specific bond in each resonance structure. For example, with CO32-, this CO bond right here, there's 2 in this, 1 in this, and 1 in this. So we add that up, that's 4, divide that by 3, and the bond order is 4/3. Solve this. Draw the resonance structures and find the bond orders in SCN-. This will be the resonance structure, and this will be the bond orders.
Alright, so this is the FRQ that we're going to work on. This is a cumulative FRQ. So the first question is asking for a Lewis structure diagram for IF3. So IF3 has 27 electrons for fluorine and 7 more electrons for iodine. That makes 28 electrons. So that means that we have to draw our central atom first, and so the central atom will be iodine because, as we mentioned before, that the lowest electronegativity will be the central atom, and iodine has the lowest electronegativity, as we can see by the chart. And so iodine goes to the middle, and then you draw fluorine 3 times, as there are 3 fluorines, and then you draw the bonds that connect all of them. This subtracts 6 electrons. This leaves us with 22 more electrons, and then you draw this other 6 electrons for fluorine to fulfill the octet rule, and that gets rid of 18 more electrons. This leaves us with 4 electrons. Now the 4 electrons will need to go on the central atom because all the octets have been filled, but the central atom can accept more. This is an exception, and so we add 2 more, and this is a Lewis structure diagram. It's not very clean, but it works. And so the second question asks to predict the molecular geometry. So as we can see by our Lewis structure diagram, there are 5 electron dense regions, the 3 bonds, and then the 2 lone pairs on the central atom. And so having 5 of them and 2 of them being lone paired, this means that this is T-shaped, and this is by our Vesper rules, and this is something else that you have to memorize. Alright, for C, it asks us to draw SO2 Lewis structures and to draw all the resonance structures for SO2 and to find the bond length and see why they are the same. So the first one will look like this, and this adheres with the octet rule. You can take a look at all of them and you will see that they do in fact adhere with the octet rule. And then like this. So as you can see, these two are resonance structures because the bonds change on both structures, but their bond length stays the same because, as we mentioned before, the average stays the same. So there's 3 bonds in both, and they're divided by 2 areas, so 3 halves, and so that means that both of the bond lengths will be 3 halves. For D, it's asking for the hybridization of the sulfur atom. And so because there are 3 electron dense domains, this middle one right here and these 2 right here, that means that it will be sp2 because it's always sp minus 1 by the amount of electron domains that there are. So this is the next question. This gives us a reaction and it tells us that it's exothermic, and it's asking us to create a potential energy graph for it. So we'll start the graph off like this for the normal version, and then we'll have a big jump, and then we must end it off below the initial point because the reaction is exothermic. So this is for the not catalyzed one, and then we can do another one for the catalyzed one, which will be the same way, except it'll be a lower bump because the activation energy is lower. The important things that you have to consider in this model is that the final should be lower than the initial because the reaction is exothermic. If it was endothermic, it would be the opposite way. And because it's asking for what would happen with the catalyst, we would have to also make the activation energy lower because that's what a catalyst does. All right, moving on to the next question. It's asking us to predict how the ratio of the pressures of SO2 and PSO3 would change when you increase temperature. So as we can see with the reaction here, temperature is nothing more than heat, and because it's exothermic, heat would be on the product side. And when you increase heat by Le Chatelier, the reactants would also be increased. And so because of that, the SO2 produced would increase. And so when we go here, the numerator would increase. And so because of that, the ratio would also increase. And how the presence of a catalyst would affect the ratio. So all a catalyst does is it lowers how much time it takes for a reaction to reach equilibrium. So it doesn't actually change the concentrations of either of them. And so because of that, the catalyst would not change the ratio at all. And this is the whole FRQ. I hope you guys enjoyed our video lecture.